Hey everyone, and welcome to this explainer. Okay, we are jumping right in today. We're stepping straight onto the construction site, and we're going to put on the hard hat of a senior quality assurance engineer. We'll be looking at this incredibly dense, highly technical 12-step standard for constructing diaphragm walls. You know, those massive, deep underground retaining walls that basically keep skyscrapers from collapsing into the dirt? Yeah, those. But look, instead of just reading you a dry standard operating procedure, we're going to transform all that rigorous documentation into a highly visual, totally actionable field guide. All right, here is our roadmap. We're breaking this down into 6 parts. Section 1, supervisor's role. 2, guide wall and drilling. 3, the steel cage check. 4, pre-pour prep. 5, concrete pouring. And finally, 6, the master quality table. We're basically following the chronological journey of a diaphragm wall. So, Section 1, Supervisor's Role, the Mindset. Let's get right to it. Before we even think about touching a tape measure or looking at wet concrete, we have to get our heads right. And our central idea here is simple. Verify every millimeter and every minute. Honestly, this quote perfectly hits the nail on the head when it comes to the core thesis of the standard documentation we're analyzing today. When you're out there supervising a diaphragm wall, precision and timing are literally everything. You're not just a passive observer, right? You are actively measuring, you're testing, and you're enforcing some incredibly strict boundaries. There is absolutely zero room for guesswork here. Okay, Section 2, guide wall and drilling, the foundation. This is our first real operational phase where we actually break ground. The absolutely crucial point here is matching the right tool to your allowable error limits. So, for checking the guide wall width and making sure it sits a maximum of 15 centimeters above the natural ground level, a standard tape measure is totally fine. But when you need to verify the central axis positioning, you've got to upgrade to a total station. And again, you're ensuring the error there is no more than 15 centimeters. Now here's a really interesting detail. When you're checking the final trench depth against the blueprint, the standard specifically mandates using an inelastic tape measure. Why? Well, think about it. A regular tape measure might actually stretch over those massive depths, right? And that would give you a completely false reading. Every single tool has a very specific purpose. All right, once you actually start digging, you're relying on a retaining fluid to keep that massive dirt trench from just caving in on itself. And the standard outlines 4 highly specific parameters for this specialized fluid, which you have to check both before and during the drilling process. So grab your specialized tools. First, fluid density has to sit tight between 1 and 1.04 grams per milliliter. Viscosity, that needs to be between 32 and 45 seconds. Your sand content must be strictly less than 1%. And finally, the pH level needs to stay between 8 and 10.5. Listen, if any of these 4 metrics start to drift, the structural integrity of your entire trench is instantly compromised. If a parameter fails, you immediately halt drilling and you cycle that fluid right through a desander until it's perfectly back to spec. No exceptions. Moving right along to Section 3, steel cage check. Millimeters matter. The trench is drilled, it's stabilized, so now we reinforce it. If you are a junior engineer, I want you to mentally grab your tape measure right now. Just imagine holding it up against this absolutely massive, multi-ton steel reinforcement cage. It's intimidating, but you have to be precise. For the spacing between the main steel rebars, you're only allowed a variance of plus or minus 10 millimeters. For the stirrup spacing, you get a little more room at plus or minus 20 millimeters. The total diameter of the cage, that cannot deviate by more than 10 millimeters. And even across the entire length of this huge structure, you literally only have a 50 millimeter margin of error. It is a game of millimeters out there. And you know, it's not just about the spacing, it's about the connections too. The documentation strictly requires a visual and physical check of the joints. For the main steel, you need a minimum of 3 ties. At the connection joints, 100% of the stirrups absolutely must be tied to the main steel. Then you've got the sonic testing tubes, which we use later to check the concrete's quality. The offset for these tubes at the joints cannot exceed a microscopic 0.5 centimeters. And just to be completely sure they're sealed properly, you actually have to run a water pressure test on them. Section 4, pre-pour prep. The clock starts. We've got an approved steel cage, and guys, this is where the pressure really starts to ramp up. The urgency here is absolute. The clock starts at hour 0, the exact moment the final desanding and cleaning of the trench is complete. From that precise second, you have a rigid, absolute deadline of 2 to 3 hours maximum to get that massive steel cage fully lowered into the trench. You cannot just take your time and stroll through this step. The standard dictates that speed and efficiency are just as critical as accuracy. As you prep for the pour, you also have to verify your equipment. Specifically, we're talking about the tremie pipe that's going to deliver the concrete all the way down to the bottom of the trench. The visual and measurement check here is defined by one golden rule. The inner diameter of your tremie pipe must be greater than or equal to 4 times the maximum aggregate size of your concrete. If you ignore this rule, your concrete is going to jam that pipe deep underground, and that's a catastrophic failure. Now, if a jam does begin to happen, the standard handling procedure requires gently lifting and dropping the tremie pipe to dislodge the aggregate, but you have to do it without breaking the concrete seal. Let's get into Section 5. Concrete pouring, the point of no return. On a construction site, this is pretty much the ultimate high-wire act. Just like lowering the cage, the concrete pour is totally ruled by the stopwatch. The standard is clear. From the moment the concrete mixing finishes at hour 0, you have to continuously maintain your slump testing, and you have exactly 2 hours, not a minute more, to finish pouring that concrete into the trench. Delaying past this 2-hour window basically throws all your safety parameters right out the window. Now commit this single number to memory right now, 2.5 meters. During the entire continuous pouring process, you've got to use your tape measure and a plumb bob to verify that the bottom of the tremie pipe remains submerged a minimum of 2.5 meters deep into the freshly poured concrete at all times. If that pipe accidentally gets pulled up too high and exits the wet concrete, the retaining fluid will instantly mix in, and the entire wall is ruined. Okay, so the pour is finally complete. Take a breath. But the supervisor's job now shifts to data verification. You have to compare the theoretical volume of concrete, meaning the exact number calculated on your design blueprints, directly against the actual field volume of concrete that you just poured into that trench. And the standard is incredibly clear on what happens next. The variance between the theoretical design volume and the actual poured volume absolutely cannot exceed 20%. If your variance is higher than 20%, that's a massive red flag. It indicates a severe issue underground, like maybe a trench wall collapsed and absorbed all that extra concrete. In this scenario, site protocols mandate immediate ground sounding and a full structural reassessment before you can even think about beginning any adjacent excavation. And hey, remember, the job isn't done just because the concrete is setting. Step 12 of the official procedure requires immediate post-pour safety measures. You've got to erect warning signs, establish a clear danger zone perimeter, and actively block all unauthorized access to the freshly poured wall section. Making sure the site is safe is literally the final step of quality assurance. Finally, Section 6, Master Quality Table, the ultimate summary. Let's pull all of these complex guidelines together. Think of this as your ultimate cheat sheet, summarizing the entire explainer today. Notice how every single operational phase connects to an exact tool and a critical limit. During drilling, you need your specialized fluid tool in hand to ensure that sand content stays well below 1%. For the steel cage, your trusty tape measure enforces that super tight plus or minus 10 millimeter margin on the main steel. When you're lowering the cage, the most important tool you have is your clock. Remember, you have a max of 3 hours. And during the concrete pour, you're relying heavily on your depth measurements to ensure that tremie pipe stays firmly submerged greater than 2.5 meters. So as we wrap up this explainer, I want to leave you with a bit of a provocative thought. If a single tolerance fails, say the sand is at 2%, or the cage is 30 millimeters off, or your clock hits 4 hours, are you prepared to halt the entire pour? Really embracing the full authority and responsibility of a site supervisor means having the confidence to look at the crew and say, stop, in order to protect the integrity of the project. It's all about owning every millimeter and every minute. Thanks so much for joining me for this explainer, and I really hope this helps you master the foundations of diaphragm wall construction.